Your funeral. Okay. So today we're going to finish up chapter 1 in the book, um, or all the little important tidbits of it. And this chapter, right, is going to be on. This chapter is kind of like a review of General Physics 2, right, and mostly focus on direct current, meaning DC current. Okay, right. And those of you who were with me last semester, I don't like the word DC, meaning direct current. To me, it's better to call it like, direct voltage instead, DV circuits. Because a lot of times what ends up happening is that you're actually keeping your voltage constant, not the current constant. There are devices out there that'll give you a constant current, all right, no matter what. But in the lab, it's generally not used that way. For example, a lot of windmills, they actually give you constant current as opposed to constant voltage. But in these smaller electronics, a lot of times it's actually easier to create a constant voltage source versus a constant current source. So we're doing most of our analysis that way. Okay, let's just get reminded of what happened Monday, right? So we kind of reviewed General Physics 2, right? We went through Ohm's law, not Ohm's law, Coulomb's law, right? And did electric field and then voltages, right? And then when we got to voltages, the idea of voltage is basically how much energy, right, per charge is being carried around, right? It's basically the potential energy. If you put 1 Coulomb charge at a place, basically the voltage is the energy, right, in joules, right? Because the SI units for charge is a Coulomb, the SI units for joule is a joule. Well, for SI units for energy is a joule, right? The SI units for voltage is a volt. Okay, so this is, think of voltage as how much energy, how much potential energy that a 1 Coulomb charge has at that spot. Okay, that's what you want to think about. Okay, and then we have these power equations, right, where power is basically going to be the current flowing through a particular object times the volt V. Okay, and unfortunately we're using this letter V in like 2 different meanings, right? Up here, V is basically the potential at a particular point. It's 10 volts here, 15 volts here, 30 volts here, negative 5 volts here, right? But in this equation, it actually indicates a voltage drop. Okay, what that means is that, right, let's say you have some device, it doesn't even matter what the device is, right? Okay, the power best dissipating in this little device that's coming out, maybe given out as heat, right? How much, does resistor, right, is proportional to basically how much current is passing through it, right? Multiply by the voltage drop, right, across that device. Okay, so whatever V1 and V2 is, the voltage drop is going to be final minus initial minus final, right? That's the drop, right? Okay, so up here on top of this equation, right, it's indicating voltages at different places, right? Where in these equation, it's actually indicating how much does it fall when you go across. Okay, so so you should be very careful about, since it's a drop, there's also like a double negative sign here, right? Is that right? Let's just make sure we learn this, okay? Okay, let's say on this side is 15 volts and this side drops to 10 volts, right? So the voltage drop from the left to the right is 5 volts, right? Okay, let's plug these numbers in just to make sure that this is actually correct. Okay, so we have 15 minus 10, right? Actually, there's no negative sign. Okay, sorry. Okay, so that's the 5 volts. Okay, right? So don't mix up these negative sign like I just did. Okay, so think about these as, okay, if you're going from high to low, you're dropping a positive amount. It's like having, okay, you fell 10 meters, into a crevasse, and then you broke your leg and stuff like that. Okay, so all these equations that we just kind of talked about yesterday, right? That's the power one, right? And then Ohm's law is for the ones that are for resistors, right? That's just I times R, and all of these equations are indicating voltage drops. Okay, So V sub R is the voltage drop across a resistor. You've got current going through it. There's also a capacitor version of it, okay, where the voltage drop across a capacitor is going to be, if you multiply that by the capacitance, you get the charge on that capacitor. Okay, it's a little wonky. It's a little bit different format for each of these. But these are the ones that are easiest to remember, right? QVC and then VIR, right? The more complicated version of it is that if you want to write everything in terms of current, right? Because we can always measure current, right? It's really hard to measure charge, right? Unless you go out there and count all the electrons around, okay? But what charge is, right, is basically the time integral of current, right? Right? If I have 1 amp of current running into a device and I'm collecting it over time, think of integration as just like, how much you're collecting, right? It's integrating, okay? Right? 1 amp of current going into this device, right? That's 1 coulomb per second that's going into this device, right? In 60 seconds, how much charge will be in this device? If I have 1 amp going into this device for 1 minute, 60 coulombs, right? So you're basically adding up all these little charges, right? And 60 coulombs is actually a huge amount of charge. And that's what this is indicating, right? This is basically how much charge. Actually, this is not correct. There isn't a VC here, okay? Basically, the amount of charge you get is the time integral of the current, okay? And we're going to see that the opposite is true for inductors, okay? The voltage drop across an inductor is equal to this, constant that we determine, right, where you can just measure it, right? But it's a derivative instead of an integral, okay? So in some ways, a capacitor and an inductor actually kind of acts in an opposite manner, at least mathematically, okay? Which is a neat thing. That's why we want to have both. That way we can, if we want to differentiate something, right, we will use an inductor. If we want to integrate something, we use a capacitor, okay? And that's how all this mathematics of the circuit element gets connected to the physical devices themselves. Okay, any questions about what we just talked about on Monday? Concerns? Okay. Oh, I also brought my the General Physics 2 textbook for those of you who used it, but then, maybe you just had the rental, so if you want to use that book, you're welcome to use that. Okay, so let's talk about some simple circuits, and that way a lot of this will be hopefully review, but there's some additional minute details that, in the General Physics 2 textbook, the textbook author was really nice and made everything consistent and the same. Okay, in the real world, when we have to work with other people, different people does different things. Okay, and then and it's just a little. You just have to realize what they mean when they draw stuff. Okay, so on this little diagram here, these are actually, depending on who drew it, could mean different things. Okay, so we have these point A, B, C, and D, right? And these hollow circles, right? Imagine them as kind of like little area that you can clip to. Imagine them as like these little outlets here. Okay, you can clip to this, right? That's what you want to imagine these empty circles to be. Okay, and these black lines are wires, right? That's connected into the device, and this black dot in here indicates that these two wires are like hardwired to each other, right? They're physically touching each other. So if you have, like, let's say you have a current going through here, this current will actually split into 3 different directions, right? Okay, if you have a current going through here, the current coming out will actually split into 3, right? Because they are, right? This is the junction of these 4 different currents. So therefore they all go in and out, okay? Right? The diagram on the right is more ambiguous, okay? Without that solid dot there, okay? Sometimes it means that these two wires are just on top of each other. They don't touch, right? It could mean this, right, where the current just flows through, or it could mean that they are connected. And you kind of have to know what the author means, okay? And in this textbook, okay, they're going to follow this convention where the dot actually indicates a connection, okay? In this particular textbook, the one Where is it? This, okay, right? And this one, okay? In this textbook, when they just cross like that, they mean they're connected, okay? Depending on which book you're using, you're gonna have a different interpretation. What I actually like to do when I do it myself, okay, right, when I draw circuits, I actually, if they are not touching each other, I explicitly do this where, it looks like a little, the wire just skips over the other, okay? And therefore, right, it's explicit that you're not touching each other, okay? So just be a little careful when the circuit diagram is like this, okay? Look at the other diagram it uses. If the book actually uses a dot, that means this means it's not touching, right? If the other diagrams are like this, that means this is actually connected, okay? So so that's unfortunate, okay? But you know, that's how you get a lot of people doing the same thing, doing similar things, and all these electrical engineering, physics, and circuits, and building quantum computers or whatever you're doing. Different people will have different upbringing, so they will use different conventions. Okay. The other thing that we didn't get to talk about last time is the Kirchhoff's junction law. Hopefully, this is something of a review from General Physics 2 also, where the amount of current flowing into a junction is equal to the amount of current flowing out. And I think in General Physics 2, I just use a river analogy, right? Where, let's say you have a river, right? You have some amount of water flowing into some reservoir, right? And then you have some amount of current that's flowing out of that reservoir. Let's say this goes to 3, right? So there's some water in here, right? If I declare that this is the current going in, right? And these 3 are the current going out, right? I instantly know this relationship where I1 has to be equal to I2 plus I3 plus I4, okay? If I have 1 gallons of water flowing into this little reservoir per second, right? 1 gallons of water is flowing out of all 3 of those combined, right, together, okay? And this is if I declare the direction of these current to be this way, okay, right? But a lot of times what happens is that when you're dealing with a circuit, you actually don't know which way the current is flowing, okay? Let's say initially I declare that the current is flowing in like this, right? That means, right, this equation is no longer valid because I1 and I4 are flowing in, right? So therefore, in this case, right, in order to obey Kirchhoff's junction law, right, the amount flowing in is I1 and I4. The ones that are going out is 2 and 3, right? Therefore, I1 plus I4 equals to I2 plus I3, right? Notice there's a slight difference between these two equations, okay? So depending on which direction you define your current to be, right, it changes, either it goes on the left side of the equation or the right side of the equation, okay? And what doesn't end up happening is that, well, after you solve the problem, and you're going to see some of these sometimes, this number turns out to be a negative number, okay? That just means you declare the current going the wrong way, okay? So you can actually just fix it afterward and say, okay, I declare this current going the wrong way. I'm just going to declare it going the opposite direction, right? And that way you always have a positive number on your current, okay? Right? In General Physics 2, I told you just, don't bother with that. Don't try to fix it because that's just confusing. But here, it's more important that you just keep all the current positive, and that way we don't have to think about, oh, is that current positive or negative, right? Once we draw that arrow, then we know which direction it's flowing, okay? All right. All right, the loop law we already talked about, right? When you go around a loop, right, the potential energy of some charge there doesn't change, right? Just like when you hike up, Half Dome and then hike back down the valley, your gravitational potential energy didn't change, right? So hopefully we don't have to. Any questions about that before I just kind of gloss over it? Okay. All right. Okay. So this is an example, and I'm going to post these notes so you guys have these examples. I think most of these examples comes from this textbook anyway. Um, so in this little example from the book, right, you have some voltage source here, right? These are, just imagine these as like batteries, right? They're just little power supplies, right? You have 2 of them here, okay? what happened is that there's like four different resistors, right? Two of them have the same value. Notice that R1 and R1, they're labeled the same. That means they have the same value, okay? And then R2 and R2 have the same value, okay? And what the book decided to do, right, is to define that, well, I'm going to call I1 in this direction. That means if that's I1, what's the current here? Can anyone tell me? It's I1 also, right? So imagine this as kind of like a little pipe, right, that's pumping water, right? All the water, whatever comes out of here has to go through here. So this is all in the same pipe. So they all both have the same current, right? But you cannot say that about this part here anymore because now there's a little split in the pipe, right? Right? Or you can, instead of thinking about water, just think about like driving on the freeway, right? So if you're on the same street with everybody else, all the cars are flowing, with the same amount of car current through that same street, right? But once there's an intersection, right, the car can split off into different directions. Okay? Right? So what the book decided to do is to declare this, right, to be going to the right. Okay? When you're doing this, don't put this little arrow here. Just draw the arrow on top of it, right? Okay? And then, and the book also decided that, okay, we're going to make I2 coming in here. And that's actually kind of smart because, right, if you think about current, right, these batteries is actually what's pushing the current along, right? So, you know, making the current go down this way doesn't make sense because it's going to be opposed by that battery, right? So the battery is actually going to be pushing the current up here, okay? So the book has this intuition of figuring out which one should be positive, right? It's okay for you to define it going down, but then what ends up happening is that after you do all the calculation and the result, you end up with a negative number, and then you have to flip it back anyway, okay? All right. All right. So how come? Who wants to answer this? How come this is also I3? How come the book automatically can write that as I3? Anyone? Maybe on the back row. I want to get a drink of water. David, you seem like you want to answer. Why? How come? How come the bottom is also I3? Where on the screen should it be the same as? Right. Well, it is the same because you have the same letters up there, right? But what's the reason for that? Remember what I said about this part, right? What did I say about that part? Right? So if you want to imagine a little pipe of water, or you're on the freeway, right? This is the same road, right? So whatever car goes through here has to go out here, right? There's no junction yet, right? If there's no junction, you're going to be on the same current path. Okay? So these are pictures, however you want to picture it. Water flowing through a pipe, cars going on a freeway, right? This is very important to actually have intuition, because if you figure out what this I3 is, and then now you're down here, maybe you don't even see this part, right? It's a much more complicated circuit. You're staring at this like, I don't know what the current here is, and then you're just going to get stuck, right? So it's very important to figure out how to relate the current from one part of the circuit to another, with either is it on the same pipe or is it on a different pipe, right? Okay. All right. And that's sort of the point of this um, um, example that I drew here. See, so there are other examples. These come out of the textbook, so I'll post these in case you don't have access to the book, right? And I'm not going to go through them, but this is basically analyzing all of this in order to figure out how much current is flowing through each part of your circuit. Okay? Okay, so let's skip through that. There's more examples from the textbook, from the General Physics 2 textbook. I think this is where these come from. Okay, so I'll just post these, and that way you guys can work through them. What I will do is to do an example from the exam. I don't know why I didn't put a space here. Okay, so I'll do an example that's not print it somewhere so that way you get additional examples, right? Okay. So in this example, we have, well, actually, those of you who were just in general physics 2 just did this problem at some point, like a few months ago. So, but let's just talk about it. Okay. So here we have a battery. Okay, and we have R1, R2 here. Let's just draw the circuit. And then we have a battery pointing this way. Okay. And then we have R4. And then R3 is going down here. And then R5 is here. Okay. Okay. Right. And this is, let's call this E. E. Okay. They have the same voltage in this case. Okay. And then, let's see. R1 equals to R3 equals to R5. So all the odd number resistors have the same resistance, and all the even ones have the same resistance of 20 ohms. Okay. So now the task is to figure out what is all the current flowing through all these different resistors. Okay. So the idea is to find, what I'm going to say is I1, I2, I3, I4, I5, where each I corresponds to a resistor, right? So I1 means the current going through resistor 1, I5 means the current going through resistor 5. Okay? Okay. 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 Let's have the people who was not in general physics 2 last semester tell me, what should I do first? What should be my first step? Perfect. Great. I think that's a perfectly valid way to start. But what's gonna happen is gonna end up defining a lot of currents. Let's just do it, since I don't think it's harmful, but yeah. So let's make I1 this way, I2 this way, right? Since we have a battery that's gonna be fighting this, right? So maybe I4, right? I4, let's make it go this way, right? That means this is also I4, right? But it's going to the left. Does that make sense? Okay. I3, maybe it'll go downward. I don't know yet, actually. We'll see if we end up with a negative number or not. Okay. And then I5, let's just, oops. Did the thing just crash? Okay. I5, let's just make it go to the left. Okay. All right. It's valid first step. Good. What should be the second step? Anyone else? What should I do? Is there anything that I should do first before doing a bunch of math? Ivan?
You can combine the resistors.
Yeah. Make the circuit as simple as possible at first, okay? So what I'm going to do is going to do this equivalent circuit, right? Right? So R1 and R2 are parallel to each other. I can actually figure out what the equivalent of a parallel resistor is, right? So I'm going to call this R12, right? That's the combination of 1 and 2 together, okay? All right? And then next thing I see, ooh, I think I'm just clicking on things that I'm not supposed to. R12, right? This R3 is kind of stuck there, but then we have a battery over here, right? What about R1, 4, and 5? Are they parallel or series, right? They're in series with each other because, right, this is on the same pipe, right? Okay. So I'm going to call that R45, okay? Right? And this R3 is still there, okay? Okay. Okay. R1, 2 are parallel to each other, right? That's the more complicated equation. I'm going to see what that is in a second here, right? This is actually 1 over R1 plus 1 over R2, all inverted. Okay. Okay. R1 is 10 ohm. R2 is 20 ohm. Okay. All inverted. So this is one. What is this? 3/20th inverted. Right. You flip this when it's inverted. Right. It's upside down. It's just 20 over 3 or equal to about 6.67 ohm. Okay. R45 is should be easier, right? What's right for when it's in series, they just add, okay? That's just going to be 30 ohm, okay? Because 10 plus 20. All right. I think I'm going to need more space. Click here. All right. So what should I do next? Any idea? All right. Now I have a slightly different representation of the drawing, right? So that's why I said, okay, it would have been, it's fine to declare those current initially, but now we have new currents we have to declare, right? So instead of dealing with 1, 2, 3s, let's just call these things A, B, C, right? I, A, right? Because 1, 2 is going to be kind of wonky, right? And this current, right, we can still call I3, but I'm just going to call it IC, okay? And then IB, okay? And these are still EMFs, okay? So what should I do next? Any idea? What are the Kirchhoff's laws? Anyone? Everyone? Which one should I use? I'm sorry? The loop law. Okay, let's do the both of you could have said either one. We could have done either one first. But yeah, let's do the loop law, right? The loop law is that if you go around in a loop and end up at the same point, your change in voltage is 0, right? So let's do this loop first, right? Let's call that L1. Okay. So this loop law tells you that, well, if I go around here, I end up with the same voltage. So let's start here, right? When we start here, right, we're gonna gain EMF amount of voltage, right? Okay, this is my starting point, right? And then when I reach R12, I'm gonna drop, right? Drop means negative, right? R12 times whatever the current is going across that resistor, right? Right, that's Ohm's law, okay? When I get to here, right, this is gonna be R3 times what? IC, right? That's the current going through here, okay? What should this be equal to? Now I'm here again on this loop. 0, right? Because you should not change your voltage when you go around a loop, okay? So I'm going to do loop number 2 also. I'm going to make loop number 2 go this way because I suspect that the current will go that way. And I didn't declare the direction of this current, right? So that's important, okay? So if I'm on loop number 2, right, and I start off at this point, let's do that in purple also. Loop number 2, right, I start off at this point, right? I'm going to drop R45 times IB amount of voltage. I go across this battery, I'm going to gain EMF amount of energy of voltage, right? I'm not home yet, right? When I go across this, I'm going to drop R3 IC amount of voltage also, okay? So at this point, right, there's technically also a third loop that goes all the way around like this, right? That could be L3, okay? But we only need 3 equations. There is another equation that we can use right away without dealing with loops. Anyone remember what that is? Junction, right? So whatever is going into this junction has to be equal to the amount coming out, right? So IA and IB are both going into the junction, right? So they should add together and make IC, right? A plus IB equal to IC. You guys see that? Okay. Right? If I have declared this current to go downward, then the placement of these will be different, right? Okay. Okay, so with that, what we can do, right, a simple way to deal with this. Okay. I see. This should be a pretty quick problem. Oh, okay. I'm actually going to do loop 3, okay? So that was the trick for this, okay? I'm going to do loop 3. So this equation came from loop 1. This equation came from loop 2. This is the junction, right? I'm going to do loop 3 also, okay? Because loop 3 is actually special, okay? Loop 3, right? Let's say I'm starting here, right? I still gain EMF amount of voltage when I go across it, right? I drop R12IA amount of current, of voltage, right? But when I reach this point, right, since I'm going opposite direction of the battery, I'm going to lose EMF amount of voltage, okay? Right? When I reach here, right, I'm going opposite direction of the current, right? Instead of dropping in voltage, I'm going to gain that. Imagine that as if the current's flowing down and you're climbing uphill against the current, right? You're going to gain voltage. Okay, so I'm going to gain R45 times IB amount of voltage. Okay, and now I'm end up on this other side, and I just want to reach this side. So therefore, all of this is actually 0. Okay, and that's what's special about this loop. The EMF actually completely cancel out. Okay, so you actually have a equation that relates, right? Basically IA to IB, right? So let's solve this equation. Okay, let's pull all this stuff to the right. So R45 IB is the same thing as I12 IA. Okay, so let's solve for, let's go to IB first. Okay, so we divide both sides by R45, R45. Okay, so IB is actually R12 divided by 45. Okay, okay, and 12 is 6.67 ohm, right? And then 45 is 30 ohm. In fact, what I'm going to do is I'm going to write it like this. 6.67. That's fine. IA. Okay. And that's going to be like 2.2-ish divided by 30. Okay. So this number here is 0.223 IA. Okay. Okay. Now we have this, which is nice, because, right, what we can do is that we know what IB is. Okay, so we can basically get rid of IB in this equation here, right? 45. Okay, so IB is, right, if we do the substitution in here, we get, let's just write it out one step at a time, since we're doing this the first week of class, right? That's what that's equal to. Oops, yeah. And then you can add these together, right? Because there's a hidden 1 in front of here, right? So this is actually 1.223 IA is equal to IC. Right, now we have an equation for IC, and let's get rid of that. Right, what we can do is plug this up into here, right, to get rid of that. Okay, so EMF R12 IA is equal to R3 1.223 IA. That's all equal to 0. Okay, now I can combine these together. Right, remember that I12 is 6.67 and R3 is 10, right? So here's basically, you know, multiplying this number by 10 just moves the decimal over by 1, right? So if you add all these together, you end up with 1.223 times 10 plus 6.67, right? You end up with 18.9 ohm times IA equal to 0. And we know what the EMF is. That's actually 20 volts. Okay, so IA you can get right away. Divided by 18.9. Okay, that's actually 1.06 amp. Okay, right. So there's just a lot of algebra steps. Let's push this down a little further. Okay. So now that we have IA, all the other currents actually pretty easy, right? Because if I plug this in here, I get IC. I plug that into here, I get IB, right? So let's just write those down, okay? So IC is just that same current, but times, it's just a little bit bigger, okay? Times 1.223, right? Because I plug in here, right? So 1.29 amp. Let's just write 3 sig figs. And then IB follows this equation, so I plug in IA in here. Okay. Times 0.223, right? IB turns out to be 0.236 amp. Okay. So now we have all the currents, but this is not the answer. Right? Right? What we actually want is the current through each of the resistors, right? Not the total, not the combined ones, right? We got I3 actually, right? I3 is basically IC, right? So that's checked. Okay, that's I3. Okay. What about IB? What's that equal to? I4 and I5, right? Okay. I1 and 2, that's more complicated, right? That's because, right, you have different resistance here, R1, R2, okay? The total amount that's going through here is 1.06 amp, but you're going to have to divide that current up somehow, okay? So I'll show you guys a trick, well, not a trick, but just a more intuitive way to do this, right? We know that R2 is 10 ohm, okay? And sorry, R1 is 10 ohm, R2 is 20 ohm, okay? That means, right, there's going to be, with the same voltage across it, right, that means twice the amount of current will flow through the lower resistance resistor than the high resistance resistor, okay? Imagine this as a one-lane highway. This is a two-lane highway. The same amount of traffic is going through it, right? You get twice the amount of cars, right? Sorry. Imagine this as a two-lane highway, this is a one-lane highway, because the resistance is inversely proportional how much stuff can flow through it, okay? Right? So that means this is going to carry 2/3 of the current, right? And this is going to carry 1/3 of the current. Make sense? Okay. So I1 is actually going to be 2/3 of IA, 1.06 times 0.667, right? Or 0.707 amp. Okay. And then I2, right, it's going to be 0.333, okay, 0.353 amp. Okay. Everyone happy about that? Okay. All right, what time is it? Let's just see if it's, all right, so this 2:44, right? So that was a long example. Let's take a break and then do you guys want 15 minutes or 5 minutes or 10 minutes? What's good for you guys?